Hello. In these videos, we are going to take a look at the integration technique known as integration by parts. Integration by parts is a integration technique that goes along with the product rule. U substitution helps us undo the chain rule. Integration by parts will help us with the product rule. So looking at the product rule in general on a specific example, suppose we have the function x times cosine of x, and we wanted to take its derivative. Well, the derivative with the product rule of x cosine x is 1 times cosine x plus x times negative sine x, making the derivative overall cosine x minus x sine x. Now, we're trying to think about an integration technique. So we're going to integrate everything here and take the integral of the derivative of x cosine x. We're going to take the integral of cosine, and we're going to subtract the integral of x sine x. For this first part, the integral of something that we're taking the derivative of is just that function itself. That is x cosine x, and we integrate something we've differentiated. The integral of cosine is sine, and we don't yet know the integral of x sine x dx. However, as I just said, we don't yet know this integral, but I've just created a equation. We could solve for it. We can add the integral of x cosine x to both sides, or the integral of x sine x to both sides. And subtracting x cosine x from both sides, we now see that sine x minus x cosine x plus c is the antiderivative of x sine x. How can we create a formula that does the same thing? So now let's look generically. Say we have functions u of x and v of x. I will try to have little tails on the u's to help differentiate between u and v, but our functions are u and v. And we have their product. The product of u times v, if I take the derivative, like we did for x cosine x, that will become the derivative of u dx times v plus the derivative of v with respect to x times u. Putting little tails on the u's to tell them apart. Now, following the steps we had, let's integrate all of that. The integral of d dx of u times v dx is equal to the integral of du dx times v dx plus the integral of dv dx times u dx. Here, our derivative and integral cancel like they did before, leaving us with u times v equals, in these integrals, the dx's cancel, and we still have a differential left. We have the integral of v du plus the integral of u dv. Solving for either one of these, specifically, I'm going to solve for the u dv, we get that the integral of u dv is equal to the integral of, is equal to u times v minus the integral of v du. Now, with all these u's and v's, that formula doesn't look like it's doing much, but if I compare back to what we already have, the x sine dx, if I said u equaled x, and dv equaled sine x dx, then taking the derivative of u, du equals dx, and v will be the integral of sine. So the integral of sine being negative cosine x. Then filling in this formula, the uv minus v du, with the formula, we would get x times negative cosine x minus the integral of negative cosine x. Well, the integral of negative cosine x is negative sine x, and suddenly we have the same exact thing with that formula. So, undoing the product rule, we get our integration by parts formula. The integration by parts formula is u dv is equal to u v minus the integral of v du. There is a follow-up question of how do we pick when we have two functions? How do we pick our u and how do we pick our dv? There is a general mnemonic for picking u based on I weight. I stands for inverse trig. So if we see inverse trig functions, that should be our u. L stands for logarithmic. A stands for algebraic. T stands for trig, and E stands for exponential. So we can pick our u based on this ordering. And once we pick our u, we take everything else to be dv. We will take the derivative of u to get a du, and we will take the integral of dv to get v. In the next videos, we will see more examples of using this.